If you work anywhere near enterprise architecture or identity management or security compliance, you know the exact kind of pain we're going to talk about today.
Yeah, it's a very specific type of pain.
It really is. You've likely been the person sitting in a review meeting just staring at a network diagram, trying to figure out how to provision secure digital signatures for a globally distributed workforce.
Without completely bankrupting the IT budget.
Right. Or bringing user productivity to a grinding halt. Because for decades, the industry standard for high assurance digital trust has been intrinsically linked to physical hardware.
Smart cards, USB tokens.
Massive climate controlled server racks housing cryptographic modules.
Right.
And we've just accepted this immense operational friction, the delayed onboarding, the lost tokens, the sheer administrative nightmare of physical lifecycle management.
Well, we accepted it because we fundamentally believed it was the non-negotiable price of true security.
Yeah.
It's the classic trade-off that has defined infrastructure for the last 20 years. We built risk models around the idea that if you want to secure a credential, you need to be able to walk up to it.
Touch the physical box it lives in.
Right. Touch it and post a physical guard at the door. But those models are currently buckling under the weight of modern operational demands.
Which brings us perfectly to the core of this deep dive. Today we are unpacking a highly specific, deeply impactful source document. It's titled 0403 2026 Reprise, How the Cloud is Redefining Digital Trust and Document Signing.
It's a fascinating text.
It is. And our mission here is to dissect the mechanics of a massive industry shift occurring at the end of 2026. We're looking at how the literal vaults of digital trust, the cryptographic keys that underpin corporate and citizen identity, are being decoupled from on-premises hardware.
And migrated directly into the cloud.
Yeah. We're going to break down the architectural realities of this shift, explore the regulatory forcing functions driving it, and analyze exactly what this means for you as you design, deploy, or just exist within these evolving digital trust ecosystems.
It's a pivotal transition because we aren't just talking about a software patch or a minor vendor migration here.
No, not at all.
Moving high assurance signing to the cloud challenges the foundational orthodoxies of cybersecurity. When you strip away the marketing layer of this transition, you're looking at a profound debate over whether cryptographic assurance can be maintained when the physical asset is abstracted away.
It's a huge shift in mindset.
Organizations are essentially being forced to rewrite their entire approach to risk, identity verification, and cross-border data management.
So let's start by grounding this in the reality of what the document calls the fortress model.
Right, the legacy architecture.
Yeah, the architecture that most large organizations are still heavily entangled in. When we talk about high-security digital signing, the kind required for legally binding contracts, financial transactions, or government issuance, the gold standard has always been the on-premises hardware security module.
The HSM.
The HSM, exactly. These systems relied entirely on locally stored cryptographic keys. You literally had a tamper-evident, FIPS-certified box sitting in your data center, and that box was the ultimate source of truth.
And if we examine the psychology of that architectural choice, it makes perfect sense in a pre-cloud context. The overarching doctrine of the era was perimeter defense. The logic dictated that the only way to genuinely secure a root key was to physically isolate it. It's an air-gapped mentality.
You put the HSM in a secure cage.
Right. You implement strict access controls, sometimes requiring multiple physical keys held by different executives just to open the rack. You monitor the power draw, the temperature, the physical vibrations of the chassis.
It's like a vault in a bank.
Exactly like a vault. The assumption was that network security would inevitably fail, so the hardware itself had to be the impenetrable fortress of last resort.
And on paper, that is incredibly secure. But the document highlights the brutal reality of maintaining that fortress. It specifically calls out the significant hidden burdens of this physical isolation.
Yeah, the operational costs are staggering.
The text categorizes them into costly operation, poor scalability, and cumbersome implementations. Let's unpack the actual operational friction here, because anyone who has managed an HSM cluster knows this pain intimately. I mean, the procurement cycle alone is a nightmare.
Oh, absolutely. Procuring an on-premises HSM isn't like spinning up an AWS instance. You're writing complex RFPs, evaluating specialized hardware vendors, and dealing with lead times that can stretch for months.
Just to get the box in the building.
Just to get in the building. And once the hardware arrives, the implementation is agonizingly slow. You have to rack and stack the physical appliances, integrate them with your existing network infrastructure, and then execute highly choreographed key ceremonies.
Key ceremonies. It always sounds so mystical.
It does, but it's purely logistical. These ceremonies often require multiple stakeholders to be physically present in the data center simultaneously to initialize the cryptographic material. It is a massive drain on expensive human capital.
And then comes the day-to-day maintenance, which the source explicitly describes as manual, inefficient, and expensive.
Because you can't just push an over-the-air update to an air-gapped HSM.
Right. If there's a critical firmware patch required by a new vulnerability, you are looking at scheduling significant downtime. You have to send specialized engineers into the data center and manually interact with the hardware.
And if you're a multinational corporation with data centers in 5 different countries, that maintenance overhead scales exponentially.
Which directly feeds into the scalability roadblocks the document emphasizes. Let's say your organization undergoes a massive merger, or you need to suddenly roll out a new secure remote access protocol for thousands of users.
In the fortress model, capacity planning is rigid. If you hit the cryptographic throughput limit of your current HSM cluster, you can't dynamically allocate more compute.
You have to start the whole process over.
The entire procurement, implementation, and key ceremony process all over again.
Right.
You have to buy more metal. It essentially forces IT departments to chronically over-provision hardware just to have a buffer.
Which is incredibly capital intensive.
Highly capital intensive. Your agility is completely throttled by the supply chain and deployment realities of specialized physical hardware.
And we haven't even touched on how this architecture punishes the end user.
Oh, the user experience is arguably the worst part.
The document draws a direct line between these back-end bottlenecks and a highly degraded, clunky experience for the actual employees or citizens using the system. Because the trust anchor was locked in a localized box, organizations had to distribute physical proxies of that trust to the users.
And smart cards.
Right. Smart cards, USB cryptographic tokens, specialized hardware authenticators.
The logistics of managing those physical proxies are just staggering. Consider the lifecycle management of a standard enterprise smart card. The IT department has to purchase the blank cards, securely encode them using the on-premise HSM, and then physically distribute them.
Put them in the mail.
Literally put them in the mail. If you have a globally distributed workforce, you're shipping secure materials internationally, dealing with customs, and hoping the package isn't intercepted.
And the friction for the user is constant. You forget your smart card at home, and you are effectively locked out of your digital workspace for the day.
Or you try to log in remotely, and you have to install highly specific, notoriously brittle middleware on your laptop just to get the OS to recognize the USB reader.
Yes, the middleware. Every time the operating system updates, the drivers break, and the help desk gets flooded with tickets.
Exactly. The security was absolute, but the system treated the user's time and productivity as entirely expendable. It was a model that prioritized the physical integrity of the key over the operational reality of the business.
It was an unsustainable equilibrium. Organizations were pouring massive amounts of operational expenditure into maintaining this brittle infrastructure, and users were constantly fighting the friction it created.
But enterprise IT is inherently conservative.
Very.
Organizations will endure immense pain if the alternative requires rewriting their fundamental security posture. Historically, it takes a massive external catalyst to force an industry to abandon a trusted, albeit flawed, architecture.
And according to our source material, that catalyst has arrived, and it comes with a hard deadline.
The 2026 cliff.
The document points to the end of 2026 as the absolute inflection point. It explicitly states that from the end of 2026, the IA 2.0 fundamental evolution is being forced upon large organizations.
That phrasing is crucial.
It really is. We know eIDAS 2.0 is the sweeping European regulatory framework governing electronic identification and trust services, but that specific wording forced upon them, it speaks volumes about the inertia within these enterprises.
It's the most critical takeaway there. Large institutions do not spontaneously abandon their multi-million-dollar on-premises HSM deployments out of a desire to innovate.
No, they do it because they have to.
They do it because the regulatory environment shifts so dramatically that their legacy architecture becomes a compliance liability. eIDAS 2.0 isn't just a minor update to digital signature standards. It is a fundamental architectural mandate.
It officially establishes the legal and technical frameworks required for high-assurance remote signing.
Exactly. It essentially tells the market that the era of mandatory local hardware is over.
Which triggers an enormous psychological shift. The document notes that secure digital identity can now migrate from a physical hardware device locked in a server room to the flexibility and scale of the cloud.
Think about that from the perspective of a CISO.
Right, a CISO who has spent the last 2 decades evangelizing the necessity of air-gapped physical possession for root keys. This eIDAS 2.0 mandate completely upends their worldview.
It demands a complete recalibration of how organizations assess risk. The mandate effectively declares that the doctrine of physical proximity is obsolete. It acknowledges that modern cloud infrastructure, with its distributed secure enclaves and advanced cryptography, can provide a level of assurance that meets or exceeds the traditional FIPS certified box bolted to a data center floor.
For organizations, the force of this evolution is the realization that if they don't adapt to this cloud-centric trust model, they won't just be inefficient.
They'll be structurally incapable of integrating with the new digital economy that eIDAS 2.0 is creating.
Okay, so if we are tearing down the fortress, what exactly are we building in its place?
The cloud RSC.
Right. The document introduces the primary architectural vehicle driving this migration cloud-based remote secure element, or RSC technology. This is the mechanism that untethers the trust from the physical location. The source explains that this model relocates the cryptographic element directly to a secure cloud environment. But let's pause and brutally interrogate this premise for a second.
Sure.
I am highly skeptical here, and I think you would be too. You are telling me that taking an organization's most critical signing keys and putting them in a multi-tenant public cloud environment is functionally secure. How does this not exponentially increase the attack surface?
It's the exact skepticism every infrastructure architect brings to the table. And it requires understanding the specific technical boundaries of a cloud RSC. We're not talking about storing root keys in a standard S3 bucket or a generic database.
Okay.
A remote secure element utilizes dedicated hardware-backed secure enclaves within the cloud provider's infrastructure. These enclaves provide cryptographic isolation at the silicon level. The key material is generated within the enclave. It never leaves the enclave in plain text, and all cryptographic operations occur inside that secure boundary.
So the cloud provider can't see it.
The cloud provider themselves, the hypervisor, the underlying host OS, cannot access the memory space where those keys reside.
Okay, so the keys are mathematically isolated in the cloud, but I still need to access them to sign a document or authenticate a session. How do I actually interface with that cloud enclave without an attacker intercepting the request?
That's where the mobile device comes in.
Right. The document notes that end users access their credentials remotely using their mobile devices. But again, playing devil's advocate here, relying on an employee's personal iPhone, communicating over airport Wi-Fi to authorize a high-assurance eIDAS compliant signature seems incredibly fragile compared to a disconnected smart card.
That is where the architecture of modern mobile devices bridges the gap. The authenticator is no longer a dumb piece of plastic. It is a highly sophisticated compute platform.
Because phones have their own security chips now?
Exactly. Modern smartphones contain their own hardware-backed secure enclaves, like the secure enclave on an iPhone or the Titan M chip on an Android. When a user provisions a credential, a secure, cryptographically bound tunnel is established between the secure element on the mobile device and the remote secure element in the cloud.
So it's hardware talking to hardware.
Just over an encrypted network layer.
And the authorization relies on the advanced biometric capabilities of the device, right? Face ID, fingerprint scanners.
Precisely. To forge a signature, an attacker wouldn't just need to intercept the network traffic. They would need to physically compromise the secure silicon on the user's specific mobile device, bypass the biometric liveness checks, and compromise the mutual TLS tunnel to the cloud enclave.
That's a massive barrier.
It is. The source document is explicit that this architecture successfully preserves high levels of assurance and trust. In many threat models, this distributed, dynamically authenticated architecture is significantly more resilient than a legacy system where a stolen physical smart card and a compromised PIN give an attacker unrestricted, persistent access.
That validation of the security model is crucial because once you accept that the cloud RSC is secure, the operational floodgates open.
Everything changes.
The document details the immediate operational superpowers this model unlocks, starting with seamless integration and centralized management. It points out that administrators can push real-time updates effortlessly across the entire user base.
Contrast that with the legacy nightmare we discussed earlier. In a cloud RSC architecture, the credential lifecycle is entirely API-driven. If the security team needs to rotate cryptographic keys, update signing policies, or instantly revoke access for a compromised user, they execute that command centrally. The policy is instantly enforced at the cloud enclave level.
There is no physical recall of smart cards.
No relying on end users to plug in their devices for an update. The IT department regains total control over the operational tempo of their security infrastructure.
And the friction of onboarding practically vanishes. The text specifically highlights remote onboarding as a direct solution to the logistical challenges of distributing physical tokens. Let's talk about the reality of identity proofing in this new model.
This is where we see massive efficiency gains. Under eIDAS 2.0 and similar frameworks, the identity vetting process can be fully digitized. If an organization hires a contractor halfway across the world, they no longer need to rely on the postal service to establish a trust anchor.
They don't mail them a token.
No, the contractor downloads the organization's authenticator app. They go through a remote identity verification flow, perhaps scanning the NFC chip in their biometric passport and performing a cryptographic liveness check with their camera.
And once the backend identity provider verifies that data, it triggers an API call to the cloud RSC.
Exactly. The RSC dynamically generates a new, highly secure credential and cryptographically binds it to the secure enclave on that contractor's specific mobile device.
That happens in seconds.
The entire process takes minutes, requires zero physical shipping, and provides a level of cryptographic assurance that meets stringent regulatory standards. It fundamentally alters how organizations can scale their global operations. They are no longer geographically constrained by the limitations of their physical security supply chain.
But the document makes it clear that we aren't just taking legacy capabilities and hosting them on AWS or Azure. Moving into the cloud is an architectural upgrade that unlocks entirely new paradigms.
It's not just a lift and shift.
No. The text explicitly shifts focus to what it calls the era of beyond basic signing. Cloud RSC architectures serve as the foundational platform for advanced features like credential recovery, electronic seals, and attribute verification.
This is where the rigidity of physical hardware truly shows its age. Take credential recovery, for example.
Okay.
In the Fortress model, if an executive loses their physical signing token, that specific cryptographic identity is irrevocably lost. The organization has to execute a full revocation and issue a brand new identity from scratch.
It's a catastrophic failure state for that credential.
Right, but a cloud RSC changes the location of the trust anchor.
Because the credential itself lives in the cloud, not on the phone.
Correct. The mobile device is merely the authorized remote control for the cloud credential. If a user loses their phone, the credential in the cloud remains secure.
They just get a new phone.
The user simply acquires a new device, authenticates through a rigorous multi-factor recovery protocol, and establishes a new cryptographic binding to their existing cloud RSE. The statefulness of the cloud allows for resilience and seamless recovery workflows that are mathematically impossible with a standalone physical token.
This brings us to the most disruptive concept in the entire document. The source connects this cloud RSC foundation to the emerging critical requirement for verifiable credentials. The document explicitly states that this technology fundamentally puts users in control of their own data.
That's a massive shift.
It is, and we need to elevate the discussion here because we aren't just talking about basic access control anymore. We are talking about fundamentally re-architecting how identity data flows across the digital economy. How does this actually work at a technical level?
Well, we have to look at how traditional identity and access management, or IAM, currently functions. Right now, your digital identity is heavily fragmented and centralized. If you want to prove your employment status to a third-party vendor, you are typically relying on your employer's centralized identity provider to federate that access. The data lives in their database. You just get the permission to use it. Verifiable credentials completely invert that model.
By moving the data payload to the user's control.
Precisely. A verifiable credential is a cryptographically signed, tamper-evident digital payload. Let's say it's a certification of your professional licensure. The issuing authority, the licensing board, signs this data packet using their high assurance keys and issues it directly to your digital wallet.
Which is secured by the cloud RSC architecture we've been discussing.
Yes. You now hold the definitive, mathematically provable record of that credential.
And this is where the document's mention of attribute verification becomes so powerful. In legacy systems, data sharing is usually an all-or-nothing transaction. If a system needs to verify my age or my clearance level, I usually end up exposing the entire database record, my name, my address, my exact date of birth.
Which is a massive violation of the principle of least privilege, and a primary driver of the data breaches we see constantly. Attribute verification, powered by these modern cryptographic frameworks, utilizes techniques akin to zero-knowledge proofs.
Meaning you prove something without revealing the underlying data.
Exactly.
Yeah.
It allows you to present a cryptographically guaranteed assertion to a verifying party. You can mathematically prove to a system that your security clearance is active or that your professional license is valid, and the verifying system receives a definitive true or false without ever seeing the raw data fields of the credential itself.
It allows for the granular dissection of a credential payload. You provide exactly the required proof and absolutely nothing more.
Right.
And the document notes that these systems are designed from the ground up to work seamlessly across borders and platforms.
Interoperability is the linchpin of eIDAS 2.0. The goal is to escape the walled gardens of proprietary centralized IAM vendors. If verifiable credentials are built on open, standardized protocols, they become universally readable.
So a credential issued in one country works in another.
A credential issued by a university in Germany can be instantly, cryptographically verified by an automated HR onboarding system in Canada. The trust relies on the mathematics of the signature and the standardized format of the payload, entirely independent of any single vendor's specific identity platform.
To move this out of the realm of theory, the source document provides a highly specific, real-world deployment. It details the solution developed by a technology company called Ubique, which has been aggressively adopted by municipalities like the city of Rotterdam.
That's a great case study.
It's a fascinating case study because municipal IT is notorious for being incredibly rigid, underfunded, and saddled with immense technical debt.
Municipalities are the ultimate stress test for identity solutions. They require massive scale, having to service hundreds of thousands of citizens, and they require incredibly high levels of legal assurance as they're processing tax documents, property records, and vital civic services.
You can't just hand out tokens.
They cannot afford to distribute physical hardware tokens to 600,000 residents, nor can they afford the help desk overhead to support those tokens.
Right. The document states that the Ubique solution allows these issuers to sign documents, provide services, and distribute verifiable credentials entirely without physical tokens.
By utilizing the cloud RSE model, Rotterdam essentially turns every citizen's smartphone into a high-assurance trust anchor. The city integrates the Ubique APIs directly into their existing municipal portals. The heavy lifting of the cryptography and the eIDAS compliance is abstracted away into the Ubique cloud infrastructure.
So the city isn't running the crypto servers.
The city doesn't have to manage a sprawling PKI infrastructure. They just consume the API endpoints.
And the impact on the citizen experience is profound. The text notes this improves access to everyday needs like housing and public services while strictly protecting privacy. If you are a citizen of Rotterdam, you aren't taking a half-day off work to stand in a queue at a government building with a manila folder full of physical documents just to apply for a parking permit.
Exactly. You authenticate against the municipal portal using the biometric capabilities of your phone. The Cloud RSE handles the high-assurance verification in the background, and you digitally sign the legally binding forms right there.
It's frictionless.
What we are seeing here is the practical application of the user-centric model the document predicted. Trust ceases to be a barrier or a series of physical checkpoints. It becomes an invisible, frictionless bridge. It fundamentally modernizes the interaction layer between the citizen and the state.
Replacing legacy bureaucratic friction with seamless API-driven cryptographic proof.
Exactly.
Okay, so we have thoroughly established the dominance of the cloud model. It's scalable, it's API-driven, it powers advanced verifiable credentials, and it solves the UX nightmare of legacy PKI. It sounds like the era of physical hardware is definitively, unequivocally over.
You'd think so.
Right. But right when you think the argument is settled, the document introduces a massive plot twist. It pivots hard and explicitly states that despite all the glorious advantages we just discussed, traditional non-cloud solutions remain the preferred choice in certain specific contexts.
The physical, on-the-ground hardware box is not dead.
It is absolutely not dead, and anyone designing enterprise architecture needs to understand exactly why. The cloud is a powerful abstraction, but it is still an abstraction.
Yes.
The document provides a deeply pragmatic counterargument, pointing out that in specific high-risk environments, organizations demand complete, absolute control over their physical infrastructure. They refuse to outsource the physical custody of their root keys to a hyperscale cloud provider, regardless of the operational benefits.
The document breaks this resistance down into 3 critical non-negotiable requirements. Let's look at the first one, strict data sovereignty requirements.
This isn't just a preference.
No, this is about hard legal boundaries. What does data sovereignty actually look like when it comes to cryptographic keys?
Data sovereignty dictates that data is subject to the strict legal frameworks and privacy regulations of the nation in which it is physically stored and processed.
For most commercial data, this is manageable through cloud region selection. You just spin up a server in Frankfurt or Paris.
But cryptographic root keys are the crown jewels of an organization. In many jurisdictions, especially within the EU, under frameworks operating alongside or extending principles from GDPR or the NIS2 directive, highly classified government agencies, defense contractors, or critical national healthcare providers operate under explicit legal mandates.
And those mandates are strict.
Very. They often state that primary cryptographic material cannot, under any circumstances, leave the physical borders of the country.
And the public cloud, by its very nature, is a distributed multinational entity.
Precisely. Even if a cloud provider promises that your data resides in a specific regional data center, the underlying control plane, the hypervisor management tools, and the failover mechanisms often cross international borders.
There's too much structural ambiguity for absolute compliance.
Organizations subject to strict data sovereignty cannot risk a scenario where a foreign government issues a subpoena to a cloud provider, compelling them to hand over access to the infrastructure hosting those keys. To guarantee absolute legal compliance and eliminate cross-jurisdictional risk, they must physically own the box.
And that box must be bolted to the floor inside their sovereign territory. The law dictates the architecture.
That brings us to the second critical reason for maintaining physical hardware-limited internet connectivity. We live in a bubble where we assume gigabit, always-on fiber is ubiquitous, but at the edge of the network, that is a dangerous assumption.
The document rightly points out that a cloud RSE is entirely useless if the network path to the cloud is severed. You have to consider tactical edge computing environments.
Like what?
Think of a deep-sea oil rig, a commercial shipping vessel navigating a remote ocean transit, or a forward-deployed military unit. These entities run massive, complex local networks that require high-assurance authentication and secure communication.
They can't halt operations because their satellite uplink to an AWS region dropped due to weather.
Exactly. If their local connection to the cloud goes dark, they cannot afford for their entire identity and signing infrastructure to freeze. They require localized trust anchors. They need physical HSMs deployed directly in their tactical environments to ensure operational continuity independent of external network availability.
They sacrifice the ease of cloud management for the absolute guarantee of localized availability.
It's a calculated trade-off.
Which leads perfectly into the third reason outlined in the source, the crucial need to mitigate vendor dependency and exposure to cloud service disruptions. This touches on a massive nerve in modern IT systemic risk and vendor lock-in.
When you migrate your root cryptographic infrastructure to a public cloud provider, you are fundamentally outsourcing your organization's ability to establish trust. You are placing your operational destiny entirely in the hands of a third-party vendor.
And while hyperscalers are incredibly resilient, they are not immune to catastrophic failure. We've all lived through those cascading outages.
Oh yeah. An engineer pushes a bad routing update in one region, and suddenly half the internet goes dark.
You try to log into your SSO portal or authenticate a transaction, and you just get timeout errors because the underlying cloud infrastructure is flailing.
Now magnify that risk. If a global Tier 1 bank relies entirely on a cloud RSE, a regional cloud outage doesn't just mean employees can't log into Slack. It means the bank cannot cryptographically sign multi-billion-dollar interbank transfers.
It means their core business halts.
Exactly. Many highly regulated, risk-averse institutions look at that systemic dependency and conclude that the operational cost savings of the cloud are eclipsed by the existential risk of relying on a vendor's uptime. They choose to retain on-premises hardware precisely because it allows them to maintain sovereign control over their business continuity planning.
So we arrived at a massive architectural stalemate. On one side of the ledger, you have eIDAS 2.0, forcing the adoption of dynamic API-driven signing and the sheer operational brilliance of the cloud RSE model.
And on the other side,
You have the immovable realities of data sovereignty, edge connectivity, and the mandate for absolute physical control. It feels like enterprises are being forced into a brutal compromise between compliance and modernization.
but the document reveals a fascinating, highly sophisticated middle path.
The hybrid model.
Yes, it introduces the concept of installing legacy hardware HSMs that have been retrofitted with modern built-in signing capabilities. This is the industry's answer to this stalemate.
The document specifically highlights a strategic partnership between Ubique and Thales.
To understand why this matters, you have to know that Thales is one of the dominant global manufacturers of these massive FIPS-certified hardware security modules. They build the literal fortresses we've been talking about.
So what does this partnership actually do?
What this partnership allows is for the advanced cloud-native Ubique signing software to be deployed directly into the secure execution environment of the physical Thales hardware.
How does that actually function in a deployment scenario? Let's walk through what this looks like for an enterprise.
Let's take that highly regulated Tier 1 European bank.
Yeah.
They legally must maintain data sovereignty. They cannot use the public cloud for their root keys. So they purchase the physical Thales HSMs and deploy them within their own geofenced data centers. They satisfy the regulators because they maintain absolute physical custody of the hardware. But instead of having to deal with the archaic, cumbersome legacy software usually required to manage that HSM, they utilize the Ubique integration.
The modern software layer abstracts the complexity of the hardware?
Precisely. The Ubique layer running inside the box provides the modern APIs, the mobile device integration, and the eIDAS 2.0 compliant signing flows. The bank's IT team gets to interact with the system exactly as if it were a modern cloud RSE pushing updates, remotely onboarding users, managing policies via API.
But the actual cryptographic execution is happening locally on their own sovereign hardware.
The text accurately states this provides all the security, reassurance, and regulatory compliance of an on-premise solution, but with substantially less effort.
It's an incredibly elegant architecture. You get the unassailable fortress, but the internal mechanisms of the fortress have been completely digitized and connected to modern workflows. It proves that compliance doesn't necessarily dictate stagnation.
It highlights a maturity in the market. The industry has moved beyond the binary debate of everything must go to the cloud versus everything must stay on-premise. The document concludes by noting that organizations now have a choice of efficient and robust solutions.
Enterprise architects can now map their infrastructure directly to their specific risk profiles and regulatory demands,
rather than being forced to bend their operations to accommodate the limitations of their hardware.
As we synthesize the entirety of this deep dive, the magnitude of this 2026 shift becomes undeniable. We are watching the foundational infrastructure of digital trust undergo its most significant evolution in decades.
It really is a watershed moment.
Organizations are systematically escaping the paralyzing costs, the scalability roadblocks, and the terrible user experiences of the legacy fortress model. Concurrently, they are leveraging cloud RSE and hybrid models to not only meet the stringent new standards of eIDAS 2.0, but to lay the groundwork for a future defined by user-centric verifiable credentials.
The central thesis we've unpacked today is that the fundamental definition of digital trust has been permanently altered. For years, trust was tactile. It was intrinsically linked to the physical possession of a metal box.
Right.
But the architecture detailed in this document proved that we have successfully abstracted trust away from the physical layer. The central question of security is no longer who holds the hardware, but rather how rigorously can we mathematically isolate and dynamically verify these interactions.
We have moved from physical trust to architectural trust.
That's a great way to put it.
And that transition leaves us with a profound, almost philosophical implication to consider. The document makes it clear that eIDAS 2.0 and these modern RSE architectures are explicitly designed for interoperability across borders, shifting us toward a model where high-assurance verifiable credentials live dynamically in the user's mobile wallet.
It erases boundaries.
It does. So I want to leave you, our listener, with a complex question to mull over, drawing strictly from the implications of the architectures we've discussed today. If these frameworks allow our highest, most legally binding forms of digital identity to float seamlessly across international borders, managed by cloud infrastructure that abstracts away physical geography, what does that mean for the ultimate concept of national identity?
That's the big question.
If your core trust anchor is no longer a physical document printed and verified within the borders of a single nation state, but instead a universally interoperable, cryptographically verified credential residing in a borderless cloud environment, do we fundamentally become digital citizens of a global network?
Or does it trigger a backlash?
Exactly. Does this exact borderless potential ensure that the strict data sovereignty laws we analyze will become the fiercest technological battlegrounds of the next decade, as nations fight desperately to keep digital identities tethered to their physical soil? It is the ultimate tension between borderless cryptography and border jurisdictions, and it is going to dictate the architecture of the internet for the foreseeable future.
It's definitely something every architect needs to be thinking about right now.
Absolutely. Thank you for joining us on this deep dive. It has been a fascinating journey unpacking the hidden structural mechanics of the digital trust systems that run our world. Keep analyzing the systems you interact with, question the architectures beneath them, and stay curious. We will see you on the next deep dive.